Şahin Şahikli, IPM, me from Eastern Mediterranean University, Turkey, İzzet Sakallı. Bayram Tekin, professor from Bilkent University, Turkey. Behnam Purasan, Damkan University, and Mir Faisal from Canadian Quantum Research Center. And among the submissions, first, the committee made a shortlist. As far as I remember, 7 submissions were in a shortlist. And the Professor Leonard Suskind's paper, which is entitled Black Hole String Correspondence, achieved the highest overall score according to the committee's evaluation. So, with your permission, ladies and gentlemen, I would like to announce that J-Hub Prize 2025 is awarded to the Professor Leonard Susskind of Stanford University for his paper, Black Hole String Correspondence. So let's applaud him.
Thank you so much.
And you got 1 billion Iranian money. I don't know its exact correspondence, but congratulations, Professor. And
that's so nice. Thank you so much. I'm very pleased.
And the next prize will be 2 years later. And second and third winners will be announced by Professor Behnam in closing session. With this opportunity, I would like to give a brief information about Professor Susskind, although everyone knows him very well. But just in a few minutes, I would like to summarize his biography. Professor Susskind was born in New York in 1940 and received his PhD in physics from Cornell University in 1965. He has authored and co-authored more than 260 influential scientific papers, together with leading physicists around the world. His works have received more than 58,000 citations, and his H index is now more than 100, one of the pioneering theoretical physicists worldwide. He has been honored with many prestigious awards, including the Holography Prize, Dirac Medal, Oscar Klein Medal, Rucht Prize, Sakharov Prize, Science Writing Award, and many. And his pioneering contributions to string theory and holography, the black hole information paradox, and quantum complexity have profoundly influenced modern theoretical physics. In addition, his acclaimed books such as The Black Hole War and The Theoretical Minimum, these are the most selling books also about the physics subject in the worldwide. So now it's my great honor to invite Professor Leonard Susskind to deliver his talk on observers in Desitter space. So, Professor Susskind, this is your turn.
I have to screen share, and I have to remember how to do that. Okay, share. Screen. I'm slow at this, so can you see my screen?
Yes.
Okay, so let me, okay, so go here. Now, do you see that? Observe, can you see,
Perfect, Professor.
Okay, let me just get rid of the, okay, are we ready? Can I start? Hello?
Yes, go ahead, please.
Yeah, I've had similar experiences to what Edward had, where my computer just disconnects. I've had the experience of lecturing for almost half an hour once to an audience which wasn't there because my computer had disconnected and I didn't know it. So what I'm inclined to do from time to time is just ask you, okay, did you understand that, or something like that, and have you answer, yes, I understood, or something just to indicate to me that I'm still connected. So somebody should keep their microphone active so that they can answer me so that I know that I'm connected. Okay, so please, somebody keep connected with me. All right, what I'm going to talk about, is the question of observers in de Sitter space. Now, when I say de Sitter space, I mean eternal de Sitter space. I don't mean inflation that comes to an end. I don't mean anything but something which is not known with absolute precision to exist, namely eternal de Sitter space that lives forever and ever. And the tall Penrose diagram puzzle. You'll see what that is in a minute. Now, I've underlined Edward's name here for the simple reason that there was a great deal in what Edward talked about that is directly relevant to what I'm going to say today. I'm hoping that you will be able. I didn't know what he was going to say, so I didn't make connections in my talk here. But I'm hoping that you will see the connections. So first of all, let me thank Edward for setting up several issues that are directly relevant to what I'm going to talk about today. Now, I've had many, many discussions about de Sitter space and the holographic principle. Generally speaking, the reaction of almost everybody that I've spoken to about this is that there is no de Sitter holography, either that there is none and can never be, or that there is none because we haven't found it yet. My answer to that is, why not? See all of my papers. All of my papers are about de Sitter holography. And I think they all make sense. So why do you think there's no de Sitter holography? And the answer tends to be, in many cases, the tall diagram effect. I'm going to explain to you as we go on what the tall diagram effect is, why it has misled people into thinking that there is no de Sitter holography, and what the resolution of the puzzle of tall diagrams is. Okay, let's talk about de Sitter space holography. On the left here, I have the Penrose diagram of de Sitter space. So let me get my laser pointer just a minute. Hold on a second. I want to find the laser point. There it is. All right, on the left here, I have the Penrose diagram of de Sitter space. It's just a square. There are two triangles to the left and right, which represent static patches. Static patches are the regions of the space here which are accessible to a hypothetical observer living on the edge of the diagram here. I'm not going to go too deeply into the geometry here. Let me just say that de Sitter holography involves the holography of static patches. A static patch is what can be seen by a particular observer. The observer cannot see what's going on here, but can see, in principle, everything that's going on in the static patch. There are two static patches, a left static patch and a right static patch. Of course, there are an infinite number of static patches. But once we select on a particular observer or a particular geodesic here to represent perhaps imaginary observer, then there's a static patch associated with that observer, and there's a complementary one on the other side of the Penrose diagram, the left static patch and the right static patch, LSP and RSP. The little blue dot here is some imaginary, either real or imaginary observer who is traveling along this geodesic here. Now, if I slice through the diagram to ask what the space looks like at an instant of time, what you'll see is two hemispheres. Two hemispheres, the center of one hemisphere, right over here, is this point over here. And if we look out from that center, we eventually see a horizon. The horizon is this point over here. So looking out from here means looking into the diagram from the edge over here toward the horizon over here. There are two static patches. So I doubled this diagram here, two of them. This represents the left static patch. This represents the right static patch. In my own view of the holography of de Sitter space, it's the holography of a static patch, or of two static patches. All right, so what is the view of the holography? The holography degrees of freedom, first of all, reside at the boundary of the static patch. What is the boundary of the static patch? The horizon. The horizon either is, on the Penrose diagram, it's just this point here. In the spatial section here that I've drawn, it's the bounding circle here. So the holographic degrees of freedom, which I'll assume are discrete, and that there's a finite number of them, I'll draw them as little red dots. The little red dots, whatever they are, we don't know with any precision what they are, they inhabit the horizon of the static patch. How many such degrees of freedom are there? Proportional to the area, and as by logic which is connected to the black hole logic, the number of degrees of freedom describing the static patch is the area of the horizon times c cubed over 4g h bar. I've included the c here. Edward did not. Okay, so that's the idea of a holographic description of a static patch, what's going on in here in terms of boundary degrees of freedom, boundary meaning the horizon of the de Sitter space. Now, as I said, for each choice of a right static patch, there is also a left static patch, and the left and the right static patch are entangled. At least that is in the view that I'm going to explain, or that I am explaining about de Sitter space. The left and the right static patch are entangled. That is analogous, completely analogous to the entanglement that takes place in the Penrose diagram of a crystal black hole. They're entangled. So here are the two static patches. I can't draw them in such a way that, well, in two dimensions, I can't really draw them realistically, but there are two static patches, two sets of degrees of freedom. Those two sets of degrees of freedom are entangled, but non-interacting. Non-interacting means that there are no terms in whatever Hamiltonian describes these static patches which couple the two of them together. Entangled, but non-interacting. This is completely parallel in many ways to what goes on in the crystal black hole, or in the in the anti-de Sitter black hole. Two sides are entangled, but not interacting. To say that they're not interacting, but entangled, implies, first of all, that the density matrix is not pure, or the density matrix of one of the static patches is not pure. And in particular, the density matrix of one static patch we can take to be a thermal density matrix describing that static patch. And the static patch is isolated. Isolated, again, means not interacting with anything else, no other system. So the static patch is an isolated system in a thermal density matrix. Now, how different is it to say a system with a thermal density matrix is isolated, meaning interacting with nothing else, or that it's a system in contact with a heat bath? A system can be in thermal equilibrium because it's in contact with a bigger system, interacting contact. How different is it to say the system is isolated? Well, not very different for most things. but the difference is seen in the behavior of fluctuations. An extreme example would be quantum recurrences, where a system returns to its initial state after a very, very long period of time. That's a fluctuation. And studying quantum recurrences, one would find an extreme difference for the system which is isolated and the system which is in contact with a heat bath. But the lesson here is the details of the spectrum of fluctuations, the details of slightly out of equilibrium fluctuations of a system do depend on whether it's isolated or whether it's in thermal contact with another system. So there is a real meaning to saying the system is isolated, but it's subtle, and in general it would be the experiments which would tell you that it's in contact with another system are difficult and involve small fluctuations. All right, I've now explained what I think the holography of de Sitter space is. It's a holography in which the degrees of freedom are at the boundary of the static patch, but the boundary of the static patch is simply the horizon. And the two static patches are entangled but non-interacting. And that pretty much defines it. What is the argument against this view? The argument against this view is very interesting. It's called the tall diagram puzzle, or I call it the tall diagram puzzle, or the tall diagram effect. So let me explain what it is. Again, here is the Penrose diagram. It's a square. Because it's a square, it means that any signal originating from the left edge over here or from the left static patch here will eventually enter into this upper triangle here. This upper triangle is where everything is exponentially expanding, but it will not get to the other static patch. 45-degree line from here cannot enter into the other static patch. This is often said, it's often said that the wormhole describing the connection between the two static patches is non-traversable. You cannot send a signal from one static patch to the other, at least if the Penrose diagram is truly a square. But calculations have been done which indicate the following thing. If two observers, one of them in the left static patch and one of them in the right static patch, send out signals, energetic signals, from sufficiently far in the past. If in the past signals were sent out by Alice and Bob, here are the signals. I'm going to take those signals to be very simple. Instead of saying Alice sends out a signal, I'm just going to say Alice jumps into the black. Alice converts herself to photons and sends them into the interior of the static patch. Here they go. Bob does the same thing. Okay. What does the energy of these signals do in the way of back reaction to the Penrose diagram? The answer is a somewhat surprising answer. It makes the Penrose diagram taller. Taller means that the vertical size becomes larger than the horizontal size. This is a direct calculation of introducing some energy at this point, over here, some energy over here, calculating the back reaction. It's not a very difficult calculation. Calculating the back reaction, and one finds the diagram becomes taller. Once the diagram becomes taller, it becomes possible to send the signal from the left side to the right side. In fact, you don't even need to send the signal. Alice herself is the signal, and that signal arrives at the other end, at the other static patch. So it appears that there's a fundamental contradiction with the idea that the left static patch and the right static patch are out of contact completely, since it's possible now for Alice to send a signal from the left static patch to the right static patch, if this tall diagram effect is real. The implication is the left static patch and the right static patch must interact. Everybody understand that? Now, answer me so that I know you're here. Hello?
Yes, Professor, we hear you.
No,
Okay.
everything is okay.
Okay. I just want to make sure I'm in that I'm in contact with you. If it is true that Alice can reappear, whatever, when I say Alice, I mean an object which has some information content. Alice's content may be a little bit different than Bob's. So what we're saying here is that it is possible, because of this tall diagram effect, for Alice's information to reappear at the other end of the Penrose diagram. Implication: the left and the right static patches must interact. The holographic degrees of freedom, if they exist, must interact. The right static patch, I'll focus on the right static patch, it cannot be an isolated system. And this argument, to my knowledge, was first put forward by LeBlanc, Marlov, and Myers in 2002. It is a direct assault on the holographic description that I've given. What's wrong with it? Well, I think the entire argument is based on misconceptions about observers. Alice and Bob are observers, and they're treated in this as foreign objects, things which are just put in on top of everything else in the de Sitter space. They're treated as foreign systems. An observer, a real observer, is a material system with sufficient, well, first of all, what is an observer? What is an observer? Let's talk about what an observer is. An observer is a material system. It's got sufficient richness to record the results of its interactions with other systems. It is composed of the same stuff as everything else, and it satisfies the same laws of physics. A true observer. It is not a foreign object for which you can make up any laws that you like, as long as they're consistent with quantum mechanics, for example. But it is an object which is made up out of the same things that you're trying to describe. An observer cannot be infinitely light or infinitely heavy. First of all, why can't it be arbitrarily light? If it's arbitrarily light, that would be a good thing in a gravitational system, because it would have no gravitational back reaction if it were arbitrarily light. But if it's arbitrarily light, then it has uncontrollable fluctuations, quantum fluctuations. Classically, you can have something be very light and not subject to quantum fluctuations. But if a system is light enough, it will fluctuate. And you don't want your observers to fluctuate infinitely. So the observer cannot be infinitely light. It also cannot be infinitely heavy in a gravitating system. Normally, I think we pretend that that observers or reference frames, anything that we use as an observer, is infinitely heavy so that it doesn't shake around, so that it doesn't fluctuate. But in a gravitating system, we can't do that, because if it were infinitely heavy, it would have infinite back reaction on the geometry. Real observers in de Sitter space, I use the word real with quotes around it, real observers in de Sitter space necessarily fluctuate because they're quantum mechanical and they can't be infinitely heavy, and they gravitate. They fluctuate and they gravitate. This is the quantum side of things, and the gravitational side of things. And we have to account for that. We cannot ignore that. One of the things that observers necessarily do is they eventually come to thermal equilibrium with the rest of the system. They decay. Any system in a thermal background will eventually thermalize. It will be absorbed into the thermal degrees of freedom that are excited. In de Sitter space, that's also true. In de Sitter space, which is a thermal ensemble, any object will eventually thermalize. And one picture of that is simply that an object placed at the center of a static patch, because of quantum fluctuations, will eventually become, well, Edward talked about exactly this. This is the upside down, the pencil standing on its end. Any such system will eventually fall off the center of the static patch and be absorbed into the horizon degrees of freedom. Eventually that will happen. How long will it take? It's not too hard to make an estimate. And the answer is that if L is the radius of the de Sitter space, the radius of the horizon itself, then the time scale for something because of quantum fluctuations to destabilize itself and then fall into the horizon is of order the radius of the de Sitter space times the logarithm of the mass of the object times L. It's not all that long. It's not exponentially long, for example. It's nothing exponential here. It's only logarithmically long. Everything will eventually thermalize, including an observer. If an observer somehow finds itself at the center of this diagram here, eventually that observer will be absorbed into the horizon. Now that's true into the future, but it's also true into the past. If you run the equations backward, starting with the observer sitting at the center here, and run the equations of motion, the equations of quantum mechanics, the equations of reversible quantum mechanics backward, you will eventually find that the observer is also absorbed into the horizon, or said in that's a time reverse statement. What one would say is maybe a little bit different. You might say, I'm sorry, I'm looking for, yeah. If the observer is here and you ask where it will go, it will fall into the horizon. If you ask where it came from, the same thing. It will have been emitted from the horizon and arrived at the center. Now, this is closely related to the white hole story. But in eternal de Sitter space, the white hole aspect is as likely as the black hole aspect, or not that, that's not the right thing to say. It is as likely to find an observer falling into the horizon as it is to find an observer being emitted out of the horizon. They're equally likely possibilities if the de Sitter space is eternal. Okay, so we have, what does that mean about observers? It means that observers are fluctuations. They're fluctuations in the de Sitter thermal equilibrium state in which an observer is emitted out of the horizon, perhaps sits at the center of the de Sitter space for a while, and then falls back in. It is much like the upside down pen. The upside down pen, you could not have the upside down pen being there forever into the past, as Edward explained, but you can have a pen which you set up in such a way that that when you start it out, it will find itself after a while standing vertically upward for a certain amount of time and then fall back down. You can try to aim it carefully so that you will get it to stand up for some period of time and then fall back down. How long a period of time? That depends on quantum mechanics. There's an upper bound on how long it can, how accurate you can be in doing that. And the presence of an observer, or when I say observer, the observer could be anything. It could be a black hole. It could be whatever you like. The presence of an observer is similarly a fluctuation which began when something was emitted out of the horizon, perhaps accidentally found itself balanced in the de Sitter space at the pole of the de Sitter space here, and then fall back in. This is a very unlikely process. It's as unlikely as finding it's far more unlikely than finding a pen in an initial state that will balance itself and then fall back down. Extremely unlikely. But nevertheless, as unlikely as they are, the presence of an observer are part of the thermal ensemble. They're not foreign to they are the fluctuations in the thermal ensemble. What is the probability that an observer exists in a given de Sitter space? The probability of an object of mass m to nucleate, be shot out of the horizon, is very, very small. It's the exponential of the mass of the object divided by the Gibbons-Hawking temperature. The Gibbons-Hawking temperature, I'll rewrite it here. It's the exponential of e to the minus 2 pi times the mass of the object times the radius of curvature of the de Sitter space. This number here, I don't know, 10 to the 19th, e to the minus 10 to the 19th, or some ridiculously small probability. And so in an eternal de Sitter space, the most likely thing is you will never find an observer. You will not find an observer. With this tiny, tiny probability, an observer may be present. The observers don't live very long. They're very infrequent. And so they're very, very, very rare fluctuations. I've drawn a time axis here, and these little blue segments here are the times at which an observer may be present, the fluctuations. Of course, this is an exaggeration. The real picture would have a much longer time axis, much shorter regions in which there are observers, and much, much further apart. Okay, now having explained that observers, meaning Alice and Bob, are fluctuations with probabilities for their presence, which are extremely small, let's come back to the tall diagram question. Here it is again. Alice and Bob in the past jumped into their black holes, jumped into their static patches, and according to general relativity or just simple geodesic counting, plus some back reaction, form a tall diagram in such a way that Alice does get to the other side. And in fact, Bob also gets to the other side. Let's come back and ask about that. Let's first ask about this process from the point of view of an isolated right static patch. What is seen in the right static patch by Bob? What happens in the right static patch? What happens in the right static patch is Bob jumps in, gets to the horizon, and at a later time, Alice appears on the right side. That's what this diagram is saying. Bob jumps in on his side, and later Alice appears on the same side. Well, can that happen? Is it possible that Bob can jump in on this side and Alice, whatever she is, appear on the other side? Very, very unlikely. How unlikely? Oh, here's another picture of it. This is other coordinates. Bob jumps in, is absorbed into the horizon. Alice, at a later time, is ejected out of the horizon. And we can ask, how likely is that? Okay, well, Is this possible, first of all, if the left static patch and the right static patch are isolated? How did Alice get to the other side? Well, that's not the question. The question you should ask is, what is the probability for this to take place? And does it match the global description, including tall diagrams? Well, yes, it is possible that Alice can spontaneously be ejected out of the horizon. It's a thermal fluctuation. Everything happens. Black holes are emitted, chairs, tables, bottles of wine, everything you can think of are emitted. If we condition on Bob's initial existence at time minus t, how probable is it that Alice, whatever she is, should be shot out of the horizon? And the answer is simple. It's the formula that I gave you before. The probability for Alice to appear on the right side spontaneously in an isolated system is simply e to the minus the mass of Alice divided by the temperature, by the Hawking temperature. This is the answer for a closed system, for a closed, isolated system. Yes, Alice, whatever she is, can appear on the right side, and she can appear with a probability, which is this tiny, tiny probability here, but non-zero. Let's ask the same question from the global point of view, not from thinking about the static patch, but thinking about the global Penrose diagram, and in particular, the tall diagram effect. Here it is again. I've drawn the same thing. And again, conditioning on Bob's initial existence at time minus t, that's over here, what is the probability that Alice will appear over here? Well, the answer is simply the probability that Alice was over here. If Alice was over here, set up in a state which she's about to jump into the black hole, into the static patch, the probability for the whole process is simply the probability that Alice was present at this time here, ready to jump in. How probable is that? The answer again is simply the probability for Alice to be present at this point here is nothing but e to the minus the mass of Alice divided by the Hawking temperature. This is exactly the same answer as one gets from the completely isolated point of view from a thermal fluctuation. In the one case, we applied the thermal reasoning to the right side here and asked what's the probability that Alice can spontaneously appear here, having been ejected out of the horizon. In the other case, we asked what's the probability that Alice is present here, ready to jump in and eventually get to the other side. The answers are the same. This agrees with the isolated result, but it can only matter, and this can only make sense if in the global picture, the diagram becomes tall. In the global picture, the only way that Alice appears over here is by virtue of the tall diagram effect. So it's not that the tall diagram effect violates the isolated character of the right static patch. The right static patch calculation gives an answer, and the only way to get the same answer from the global point of view is that when Alice jumps in on the side here, she creates a tall diagram. So the tall diagram effect is necessary for the agreement between the two pictures, the global and the isolated picture of the static patch. So that's to state it again, the tall diagram phenomena in the global description is essential for the agreement with the isolated right-hand static patch description. That's my conclusion. And Now we can be a little more detailed. I'm not going to try to be very detailed quantitatively, but we can also ask, for example, whoops, something happened. I seem to have what's happening now? Hello.
Actually, we see your screen,
I don't know
computer
what
screen.
happened.
Yeah, maybe you have to reshare.
All right, let me stop the sharing. Hold on. You are sharing screen. Do you see my screen now?
Yeah, I think it's coming.
Okay. Hold on, let's see. You see that?
Yes, now it's okay.
Okay, so there's a little more detail that we could talk about. We could talk about correlations between Bob and Alice. Bob jumps in and Alice reappears, or appears on the right side here. If we just take the event of Alice appearing to be completely statistically independent of Bob jumping in here, we're making a little bit of a mistake, because when Bob jumps in here, there may be a little bit of memory that Bob had been here. Over some long period of time, that memory will fade, but if that time here is not infinite, there may be a bit of correlation between the event of Alice appearing here and Bob having jumped in over here. These are just simple correlation functions. Let's see. Again, they're just correlation functions, for example, between Bob's degrees, between what's known about Bob and what's known about Alice at a later time. These correlation functions will not be zero if the time between Bob and Alice here is not infinite. Can we understand those correlations in both the global and the isolated picture? Okay, so here is, from the isolated picture, there are simply thermal correlation functions. Thermal correlation functions which correlate events over here with events over here, just correlation, normal thermal correlation functions in thermal equilibrium, and they correlate Bob's presence with Alice's presence. How do we see anything similar from the point of view of the global description based on this full Penrose diagram here? Well, here's the answer. Because the two sides are entangled, I haven't used much about entanglement now, but now we're going to remember that the two sides are maximally entangled, are fully entangled. Because of that, the presence of Bob over here as a fluctuation, but let's say the presence of Bob over here is necessarily correlated, or not correlated, implies the existence of a identical replica of Bob on the other side. If this occurs at minus t, then Bob prime must occur at plus t. This is the nature of entanglement, of maximal entanglement. If you find anything on one side, you must find the same thing on the opposite side. And if you work it out in detail, it works the following way. If you find something present in the system at a particular negative time here, you will necessarily find the same thing present at the opposite time, plus time, on the other side. That's the nature of maximal entanglement. So if Bob was present over here, Bob prime, an identical Bob prime, will be present over here. But now that Bob prime and this Alice over here, the one who is going to jump in, will be correlated simply by thermal correlations on the left side. Bob prime and Alice over here will be correlated in such a way that when Alice jumps in, there will be a memory of what appears over here will remember that Bob Prime was here. But Bob Prime being there is simply the reflection of Bob being here. The bottom line is it's possible to calculate correlation functions between Bob and Alice here in the global picture by simply using the fact that Bob over here necessarily implies the existence of an equivalent Bob on the other side. Let me summarize. There does not seem to be any conflict between the tall diagram effect. In fact, it's necessary, the full tall diagram effect, in order to make consistent the global picture and the isolated right static patch picture. This is all based on the idea that observers are not things that you just add in, are not foreign objects that you just add in, whose equations and whose laws you can make up. They're material systems composed of the same stuff as everything else and satisfies the same laws of physics. This rarely comes up in ordinary physics, but I think in the closed system of de Sitter space, it's necessary to remember that all the objects which can be described in that de Sitter space all originate from the same holographic description, including the observers who can make observations. In de Sitter space, observers are very rare fluctuations, but they are implicit features of the thermal ensemble. When account is taken of the rarity of these fluctuations and the probabilities for these fluctuations, at least up to the present time, it seems that the tall diagram effect, as I said, is completely consistent with the isolated description of the right static patch and is in fact necessary to make them the same. Now, I realize this is difficult to follow. It's a difficult idea. It's the first time I've presented it. It will take, I think, some time before it is absorbed into the understanding of de Sitter space. In particular, the idea that the observers are part of the system and are described by the same equations. But I expect that this will happen, and that the holographic theory based on isolated left and right static patches will turn out to be the right way to think about de Sitter space. Can we prove that? Certainly not at the present time. So anyway, that's what I had to say, and thank you for your time.
Thank you, Professor. It was great.
And I'm here to answer questions.
There are some in the chat board. One is from Fabiano.
Yes. Thanks, Professor, for the nice and strong talk. It's a good pleasure see your presentation because I follow your works and try to do other works using other gravity theories, of course. But my question is about how connect the Alice and Bob using other ways. But you respond this because you're talking
Wait,
about the possibility of
I'm sorry, I had a little trouble understanding the last few words that you said. Can you repeat what?
yes. My question is about how we can to connect the Alice and Bob. But you respond this because you're talking about the possibility to use the replica trick, the double holograph model,
Mhm.
to connect the both sides of the black hole. And my question is about this, but your response in the almost the end of the presentation.
Well, I'm not exactly sure what the question was. There are two kinds of connections we can imagine between Alice's side and Bob's side. One of them is entanglement. The other is dynamical interaction between them, coupling in their Hamiltonians. Entanglement between Alice and Bob's side is implicit in the holographic description that I've described. And it seems that really it's only entanglement which is necessary to explain. We're not explaining the appearance of Alice so much as we're explaining the probability for the appearance of Alice on the right-hand side, where everything in quantum mechanics and everything is probabilities. The only reasonable questions we can ask from the right side is, what is the probability that Alice appears over here? That probability is very, very small from the isolated point of view. Just an isolated system, the probability that an Alice will suddenly spontaneously appear is extremely small. But if observers were eternal things that sat there forever and ever, and we could say with probability 1 that there was an Alice here and Alice ready to jump in here, we might conclude that there's a high probability for Alice to appear over here, and that would be inconsistent with the isolated description, which says that the probability is extremely small. However, if we take into account that Alice is herself a statistical fluctuation or a thermal fluctuation, and ask what is the probability for that fluctuation for Alice to exist, then we find complete consistency between the probability that Alice appears here as calculated simply from the isolated thermal properties of the right static patch and the description in which Alice appears as a fluctuation, jumps in, and then the tall diagram effect makes it possible for Alice to appear over here. So, as I said, the probability for the event is the same in the two descriptions. One would really like to show that all probabilities are the same. Everything, every probability, multiple Alices, correlation functions, the whole works, are identical in the static patch isolated system and in the two-sided system. And I think that's true. I just illustrated the idea with one particular example, namely the probability for Alice to spontaneously appear. I don't know if that answers your question or not. But it's about all I can say.
Yes. Yes, it is about this. The way to the information. But okay, thanks for your answer.
Yeah, okay, good. Thank you for the question.
Can I ask a question? Could this framework be extended to time-dependent backgrounds? For example, like Friedman-Robertson-Walker universe?
That's a good question. That's a good question. I don't know. Of course, much of what I said here has to do with the properties of equilibrium. Equilibrium means time independent. And one of the key properties of de Sitter space, and I say eternal de Sitter space, is that it's an equilibrium system. So your question is, I think, a good one, but frankly, I don't know the answer.
Thank you.
Any other?
I want to ask a question. Thank you for a clear explanation, Professor.
No, I'm not sure how clear it was. I recognize that there's a very, very unfamiliar ideas here. So I'm not sure how clear it was, but thank you for saying it was clear.
My question is, Where does the temperature come from if the whole system is isolated?
The temperature, okay. Where does, well, we have two systems which are entangled with each other, the left and the right. If we only look at the right side, we have to integrate out the left side. Integrating out the left side, what does that mean? It means that we construct the density matrix of the right side by summing over all the possibilities on the left side. The global state of the system might be a pure state, but the state of a subsystem, which happens to be entangled with the other side, that will necessarily be impure. And for de Sitter space, one can calculate what the properties of that impure density matrix are. They're thermal, and they're thermal at the Hawking-Gibbons temperature. So this is an old story, calculating the properties of a single static patch by integrating out the complementary static patch. And keep in mind that the complementary static patch cannot be seen from the right static patch, and therefore it makes perfect sense to integrate it out and to ask what can be seen in the right static patch, and the answer is an impure density matrix, which is thermal.
Thank you.
The same thing, incidentally, is true for the Kruskal black hole. The Kruskal black hole also has two sides like this. The global state of the Kruskal black hole is pure, and the state associated with what's analogous to the right static patch, that is a density matrix at the Hawking temperature.
Yeah.
So
Thank you.
thank you.
Any other question? If not, I have. Yeah.
Yes, sorry, Prof. I have one, if possible.
Yeah.
Yeah, sure. Sorry, my question maybe is maybe stupid question, but it is related to how we can cure, for instance, the problems that Big Bang Theory faced. One of them that is, for example, horizon problem. If we consider, instead of inflation, such entangled particles that they lived in a patch that they have information about each other, and then after expansion, after the Big Bang, they already knew about each other. So if we accept such suggestion, I don't know, it can be considered as, at least for this horizon problem, as a primary solution, or no?
Okay. I don't know how to answer that, but there's something I should have said at the very beginning. I am talking now about eternal de Sitter space. Eternal de Sitter space is not a reasonable theory of the real world. It's based entirely on fluctuations. It's just a theory of thermal fluctuations in a thermal background. The real world does not behave that way. The real world is described, the real cosmology is described by something entirely different, where in the remote past, the entropy was very, very small and evolved into the high entropy state that we see today in a way that's not consistent with thermal fluctuations. I did not mean to suggest that the real world of cosmology is described by eternal de Sitter space. Why are we studying it? We're studying it because it seems to me a first step in trying to understand a world that we live in, which is much more, or will evolve into something much, much more like de Sitter space than anti-de Sitter space. The main purpose here was to get to learn about a new kind of space-time, which is what our world will eventually evolve into. But this is not the description of our world. Our world may be described by something more like eternal de Sitter, like eternal inflation, and that is not captured by this picture. So I'm not sure exactly precisely what you asked, but it seems to me it had to do a great deal with real world cosmology. Am I correct?
Yeah, yes.
And this, you're right. And this question of a description, a holographic description of eternal de Sitter space is just too simple to capture that. So I have nothing to say about it that hasn't been said before. I happen to like the ideas of eternal inflation and multiple bubble formations with many de Sitter spaces being produced, but that's an entirely different set of ideas. That
Yes.
so that's what I would say about this.
Yeah, thanks a lot. Thank you very much.
Any other? Professor, I have one. I'm trying to understand uh, the subject. Maybe the question could be dummy, but I want to ask, actually, I type it into the chat box, but let me express my question. Because you shared one picture with a probability formula. Over there, in your black hole complementary picture, Alice's experience, as far as I see, depends on the reference picture.
You said there was a
She
picture.
sees not. There was one probability formula
Yeah, there's
just
one
under
probability. Yeah, it's all one simple one probability formula. Here it is. This one?
Yes, we go there. Anyway, she sees nothing special while passing the horizon, but Bob will see her thermalizing. But
Well,
this
wait.
this probability
wait. Bob sees her not thermalizing. He sees her spontaneously ejected out of the horizon. This is the analog of the white hole effect. The emission of Alice is analogous to the emission from a white hole. Now, the reason that the story is different for black holes and de Sitter space is because real black holes are not eternal. They're formed in the past by collapse.
Yeah.
And if de Sitter space, if it is eternal and in a theory which is reversible, time reversible, it is just as likely to see Alice ejected from the horizon as it would be to see her spontaneous. Well, it's equally likely to see an Alice being ejected and falling into the. So this is the occurrence of Alice here is the analog of the white hole effect. It's very, very improbable, but the point is it's equally improbable when studied from either the global point of view, including the tall diagram effect, or from the more localized viewpoint of the static patch, or the isolated static patch.
Okay, Professor, thank you. Now it's more clear for me now. Thank you very much.
Yep.
Is there another question? If not, let's thank Professor Leonard Saskins once more. It was the last talk, but according to me, very much more valuable one. Thank you, Professor.
Okay, thank you. Thank you. I enjoyed it. And I would have enjoyed it more if I could have been with you in person, but Zoom will have to do. Okay. I'm going to disconnect now.
Thank you.
Perfect. Behnam.
Thank you so much.
Thanks so much.
Okay, thank you, Professor. Bye-bye.
Bye-bye now.
Okay, thank you, Professor Izzet. It's too late, and if you let me to summarize the conference a bit, and let me first stop record.